Friends, tutorial section C1. This is the problem number 4, which I had not discussed it in the tutorial, and I thought it requires some discussion, so I'm uploading this. I hope it helps. Okay, let's go through the first statement of the problem. Problem is that you define an area vector, okay, the way this is the definition, that if you take a surface and sum over all the dAs over that surface, then resultant is we can call it a vector area. All right. This is very useful in this course because, as you can see, we use dA integrals very often, and later you will see that magnetic dipole moment calculation, this is very essential because a current loop, the area enclosed comes into the calculation of the magnetic moment. But that as it may be, let's have some results of this, okay? And these are some important consequences. So once this is defined, then first we can see a physical example of what it means, for example, for a hemispherical surface, A, all right? And then we can show that this A is 0 for any closed surface. The area vector is 0. And then is the same for all surfaces sharing the boundary. Okay. And this is almost like a definition that area you can show that it is in half r cross dl. dl is the differential wavelength over the whole boundary. Okay. Then the last part, which is suppose C is a constant vector, then C dot R, projection onto its position vector, integrated over dl, is nothing but A cross C. So these are the 5 parts that I'll go through quickly. But before doing that, there are all this become very simple if we take 2 corollaries of the theorems that we have already done. They're very important corollaries and very straightforward. Let me first discuss that. Okay. So these I'll call it as important integrals concerning the gradient of a scalar t. Okay, they are corollaries of the fundamental theorem. You remember, of course, the fundamental theorem of gradient. Okay, that is a line integral. Okay, then it is path independent and depends only on the limits a and b. Okay, now can we think of integrals of the same gradient but over the volume integral? Okay, what is that? And the corollary will tell you that it is indeed the scalar calculated over the surface area S. That's the corollary 1, I call it. So integration of the volume integration of the gradient, okay, is equal to the scalar's value on this surface, integrated over the surface. Okay, and so you see the involvement of dA here. Okay, so similarly for corollary 2 is the scale del cross t dot over the surface is the integration over the surface. Okay, is minus of the line integral of the scalar t over the curve dl. These are 2 corollaries. Okay, so you can see these 3 as one set of theorems. Okay, this is line integral, this volume integral, this surface integral. All right, and these are the same form. That is, integral over the volume goes to corresponding integral, surface integral, the border, and surface integral goes over to the boundary, that is the closed curve. Okay, that defines the surface. So I'll quickly prove this corollary 1 and corollary 2. Okay, and then this is make it useful to solve that problem. Okay, and since I'm doing it separately, you can remember them and use them. Okay, in fact, so let's the corollary 1. Okay, so corollary 1 is this, that is over the volume, it is goes to the surface. So what one of the technique here is introduced to be able to use the divergence theorem or Stokes theorem to obtain relations between scalars. You make it a vector. Okay, so you let C be a constant vector. So introduce a constant vector. What is a constant vector? For example, all the unit vectors are constant vectors. It could be I, J, K. Okay, so let C be any constant vector. So, and then I define a vector function. Why am I defining this? because then I can use my divergence function, divergence theorem, and Stokes theorem to do that. Now let's take divergence, because there's a volume involved here. All right, you can see that there's a volume. So if it's volume, then probably it's best to go around, and it looks like a divergence theorem. All right, and hence I convert this grad to obtain this grad of t. I can first convert this to a vector function ct, and then take divergence. All right, so divergence of v, of course, this, and now I can say that, well, uh, this is c gradient of t plus divergence of c, but divergence of c is a constant vector, so divergence of c must be 0. So divergence of this v simply is, okay, c dot grad t. All right, now I invoke the divergence theorem. All right, so divergence theorem then, del dot v over d tau over the volume. And so, of course, I'm not writing every time, but you can always add volume here, and so on. Okay, so then I do that, and then I already, so this, I'm using this the divergence theorem. So dot ct must be ct dot da. All right, so now divergence of ct, okay, we have just proved that is c, uh, this is c grad t. This is only this term survives, and so I'm put in here. And this is being a constant vector c, okay, I can always take it out of the integral. So you can see I'm getting my t dA here. This is the right side part, right? And this is, of course, c. This is also a constant vector, so I can take that out. What it means is this technique of using a constant vector. So suppose I take this integral, then I could make c as I, and this will be I. So that will be the ith component of this integral, and ith component of this integral equal. Similarly, j dot this, j dot this. So jth component also is the same. Kth component is the same, which means these two integrals must be same. And that is the theorem QED. Okay. So I could say I have proved QED. So what is important is the statement of the theorem and making it a word format so that you remember this. All right. Okay. So that is the corollary one. I hope it's okay. Now let me go to corollary two. What we have to prove is, now we had this is over the surface. Okay, over the surface S, and that converts into a the scalar line integral across dl. There's a minus sign here. The same old technique. Okay, let's use c be a constant vector, and then v is ct. Now, of course, it's a surface integral to be related to line integral, and obviously we need to use Stokes theorem, and for that purpose only we have made constructed this vector function by multiplying a constant vector. So Stokes theorem will tell me that del cross v, okay, dot dA is v dot dl over the curve C, okay, um, over the curve, closed curve C, line integral. Now replace my v, okay, replace my v to ct, and now del cross ct must be equal to, by Stokes theorem itself, is ct dot dl. So right hand side I already have ct dot dl. The left hand side is from the Stokes theorem. So del cross ct, how do I use del cross ct? Del cross ct, I can use this product rule. I don't know which product rule is, probably product rule 7. Okay, del cross f function a is f del cross a minus a cross gradient of f. So in this case, this is t del cross c minus c gradient of t. All right. Okay, so now what is del cross C? C is a constant vector. So the curl of C must be 0. So what survives is only this. Okay, so del cross CT. So del cross CT, then this minus, so that this is minus C cross grad of T dot dA, and on in this side, it is C is a constant vector. So I can take C out, right? Okay, C dot, just like last time. And hence I can also do this is cross dot, right? C cross del T dot dA. I can always use my A cross B dot C is A dot B cross C, then this becomes C dot grad T dot across dA. All right. So now both sides have a constant vector, and minus side I have taken this. So C dot this integral is equal to minus C TDL dot of that. So obviously these two are equivalent, and hence we have proved the theorem. Okay, so let me write down the theorem in its final form. So that is, over the S, if the gradient of the scalar cross dA, okay, is equal to minus of line integral of this scalar over the curved path T. Okay, so this is a very useful, and we'll see its use in proving one of the, so this is the corollary 2. Okay, I'm restating it after having proven it. So proof has been simple. So these are the two corollaries we are going to use, and then all our, part problem 4, the proofs can become very, very simple. Let's go ahead. Okay, so first part of the problem is find the vector area of the hemispherical ball. Okay, so hemispherical ball. So, and of course, what is already known, this is the definition. So I'll write down my dA. So dA will, of course, involve is over the surface. So R is a constant. So R d theta is in this direction. Okay, and R sine theta d phi is in the phi direction. And of course, it is perpendicular to the surface, and is R hat, right? So now I want to integrate and get the vector area A by dA. Now, where is the vector? Vector is in the unit vector R. And how can I, so it's simple. I can convert this R vector into my ijk here. Why is that? Because that's simple to do. So let's see, if it is R vector, then what is its I component? Take the, this is theta, okay? So this is theta, and hence this component is R sine theta. R is unit vector, so it's sine theta. So sine theta cos phi is my x component, okay? Okay, and sine theta cos phi, this is phi, okay? Cos phi is my y component, okay? So sine theta cos phi is my I component, sine theta sine phi is my j component, and cos theta is my k component. So I put, instead of r, this in terms of ijk. Okay, so this is r square, sine theta comes from here, d theta d phi. And what are the integration limits of d theta? D theta is, of course, theta goes to 0 to pi by 2 for the hemisphere. Okay, and phi, of course, goes full, so 0 to 2 pi. Okay, so you can notice that there will be no contribution from, as you can already anticipate from the symmetry of the problem, that there will be no contribution from the cos phi and the sin phi. Okay, so here I have made a mistake. Let me write down here in terms of, this is sin phi. All right, so they are cos phi and sin phi over the whole 0 to 2 pi. So these two would not contribute, okay, because they become 0, okay, full. And this is, so what survives is only sin theta cos theta k d theta. So just d phi would give me 2 pi, okay, sine theta cos theta k, and so sine theta cos theta k, that is simple integral. So that is only pi r square. This is the area of the disk, okay, projection of the sphere onto the xy plane, okay, and its area vector is in k direction. Okay, so it's a spherical surface, but vector area is only its projection on the xy plane and pointing in k direction, because all of the components throughout are canceling each other, as you can see that. Okay, the xy component are canceling. This is clear from the symmetry as well. But going through the vector, integration is an important way of confirming our intuition. Okay, that's the first part. Now the second part, the B part, it says that so that for any closed surface. Okay, now I invoke corollary 1. You remember corollary 1? So this is the left side part, the volume integral of the gradient, okay, is equal to the surface integral of that volume. Okay, so this is the surface integral of that volume of TdA. Now what is required is A is actually is a left side, okay, with t is equal to 1. Then this is what I want to show, okay. And of course gradient of a 1, okay, a particular constant is 0. So gradient, so if from this corollary, the first corollary, the dA is equal to 0 for any closed surface. One line proof. All right. Then the okay, there is a C part also. Let me first do that. C part is if they are the same, if they convert the same boundary. Okay, so let me suppose there is a C part. Okay, so if it is the one curve, okay, with boundary, and there are two. Suppose they are not the same, then the vector for this would be, let's say, A1, and this would be A2, and which means we are assuming that A1 is not equal to A2. But I can always close this two surface with another surface, okay, with the same surface will close both. Okay, so then the closed surface, we already know that it is 0, the last result. Okay, for or both closed surfaces, it is 0. Okay, which means, okay, A1 and A2 cannot be equal to A1 and A2 cannot be different. Okay, because A1, this closed surface is 0, and A2, this closed surface is 0. Okay, so for the same boundary, A1 and A2 are the same. Same boundary, the surfaces A1, okay, must be equal to A2. Simple contradiction, contradiction argument. The D is so that A is this. Okay, so if you just take, okay, if you take any, let's say the surface, okay, I can take to the origin, and the origin O, a cone of that surface, and then any DL, okay, so this is my DL, and then DL, R plus DL is this, and this is R to the origin. So area of that is, so dA, area is, of course, half R cross DL for any small element, okay? And integration of that, it is as simple as that, okay? Integration over the closed curve over R cross DL, because R cross DL is the area of this. And what is RDL? Okay, why is it half? Because R plus DL is the area of the parallelogram, right? So total area then is simply half R cross DL. Simple. All right. Now the last part, which is, let me write it down, okay, is